everyone. Today we're going to talk about how to implement data visualization methods to help design a bushfire control system. In 2019, there is a catastrophe wildfire overwhelms the New South Wales and Eastern Victoria in Australia. It burned 243,000 square kilometers, caused a loss of about 78 to 88 billion dollars, which equals to 18% of the amount of GDP of Victoria in 2020. Also, millions of people as well as wild animals are suffer from this catastrophe wildfires. With the hotspot data provided by NASA satellite, we could count the number of fire events from 2011 to 2019. The line chart here shows the number of fire events in each season. It's not surprising to see that most of the climates are occupied by autumn. However, as for summer dogs, there are only 2 peaks, and most summer dogs has a quite lower number of fire events. In addition, visually, the number of fire events is strong seasonal, so we could use the improved seasonal series to fit this curve. It seems that the seasonal series could fit the real data well in most cases, and we could use it to focus future fire event number. However, if we plug in the data of the summer in 2019, during which is the catastrophe wildfire, the number of fire events is nearly 7 times of the predicted data. And that's why we also call this wildfire as Black Summer. In such cases, experience and modeling could not stop the disaster. Hence, we need to build a fire control system. The main components of the control system are supply stations, which control drones to surveillance or help extinguishing fire. And we apply grid abstraction to help design the station locations. There are totally 73 grids to cover the Eastern Victoria. In order to calculate the weight of each grid, we first pin all the hotspots in the past 9 years, from 2011 to 2019. Then we could discover that there are several clusters of areas that has frequent fire events. Then let's zoom in to one of these areas. And let's see this in the Google Map. As we can see in the map, this area is close to the coastline and is national park, which is mainly covered by the forest. Now let's bring in one more factor, which is altitude. To some degree, it implies the forest coverage rate together with the difficulty of fire monitoring. We take out each grid and calculate its weight by the number of hotspots and the average altitude in it. And in this map, the numbers are the IDs of grid. Rather the grid, higher the fire risk. And the topology map also indicate the altitude. We do some analysis on the altitude data. From the QQ plot, we could observe that the altitude data stick to the straight line, which means those data obey the Gaussian distribution. Since the altitude data are Gaussian distributed, we implement the hierarchical clustering. We first use elbow method to determine the number of clusters. Then we could find the elbow point at about 4, which means choosing 4 clusters is suitable. Then we do the hierarchical clustering. There are 3 main groups. red for low altitude, high risk, yellow for high altitude, medium risk, and blue for low altitude, low risk. Here, the fourth group is a single outlier, so we just simply consider it as yellow one. Finally, we tie those grids to the map, and we could design the locations of supply stations using observation or algorithm, which might place stations at suitable altitude for the convenience of surveillance and should cover all the areas, especially the red grids. And here is one of the possible solutions. To conclude, fire event forecasting based on experience or model is not enough for preventing accidental catastrophic fire. So we could build a drone-based fire control system with some visualization skills to help handle the fire situation at first time, in order to protect the environment and the common home of both people and animals. Thank you for watching this video.